Hello, everyone. We are researchers from the Chinese University of Hong Kong. I'm Renzhe Huang. The presentation title is AEON, a method for automated evaluation of NLP test cases. We all know that neural networks also suffer from bugs. Therefore, testing neural networks becomes increasingly important when more and more neural networks are being applied to real-world applications. Since constructing test cases manually is labor-intensive, various automated testing techniques have been proposed. However, in practice, many of them perform badly. They generate sentences without fluency or sentences that cannot preserve the semantics with the original ones. In addition, each paper uses its own evaluation on the generation quality, making it hard to compare the generation quality among different testing methods. With these problems, our motivation of this topic becomes clear. We want to see exactly how far are we on the direction of testing NLP software. We begin with the difference between the text domain and the image domain. The characteristics of languages are different from images. For an image, it is hard to change its intrinsic nature. As an extreme example, some testing methods in the CV area may perform patch attach, which occludes parts of the original image. But for we humans, it is easy to recognize this stop sign, even when many pixels are changed dramatically. In other words, perturbation on an image will not change what the image is. Therefore, we can assume that test cases always preserve the original labels. But for text, things are different. This example is from the movie review dataset. The testing method finds a test case by changing the word frustrating to sparkling. You can see the original text is negative, while the generated test case is positive. However, current testing methods automatically assume test cases preserve the same semantics with the original texts and also preserve the same label. This assumption can cause problems which will not appear in the CV area. Let's see what's going on during the process. If we have an original text with label 0, under some transformation, we generate a test case. But unfortunately, the test case does not preserve the semantics, and it has a different label 1. After feeding it to the model, we get the output of label 1. And now the algorithm finds that under the transformation, the model outputs a different result, and the algorithm thinks it finds a bug successfully. However, the model does not go wrong here. The model should output label 1 because the semantics has been changed during the transformation. Therefore, this is a false alarm. We call these cases that cannot preserve the same semantics inconsistent cases. Another problem is that the generated test cases are not natural or fluent enough. The transformation in the CV area has a property, that is, the artifacts are hard to detect by humans' eyes. We cannot tell the difference if the test cases is constrained using L2 norm. For texts, many testing methods can easily produce obvious artifacts. Consider the following example from York dataset. The substitutions introduce many weird grammars. Humans can easily tell the whole sentence is abnormal. We call these cases that introduce weird grammar or spelling errors unnatural cases. Since text data have the above-mentioned nature, a question arises here. How many test cases have inconsistency or unnaturalness issues? Is current NLP software as vulnerable as what previous papers thought? To answer this research question, we select 4 popular testing methods and generate test cases on 5 different datasets across 3 different NLP tests. After that, we hire annotators to evaluate the quality of the generated test cases. This is the result of the human evaluation. We can see only 15% of the test cases are marked as high-quality ones, which do not have the inconsistency or unnaturalness issues. 71% and 57% of them are inconsistent and unnatural ones, respectively. The most important thing is that 44% of them are false alarms, which means that NLP software is more robust than previous papers thought. The next step in this topic is to discover what goes wrong in the process of generating textual test cases. In other words, what causes their bad quality. We revisit the generation process and find out the constraints play an important role in deciding the quality of the substitution candidates. In other words, constraints decide whether the word can be used. Therefore, which constraints are responsible for the 2 issues? Here are some commonly used constraints on semantic similarity. They can be roughly categorized into 3 types. First, corpus-based, for example, blue. Second, knowledge-based, for example, literal. And finally, DNN-based, such as InverSend, SentenceBird, SimCSE, and BirdStore. Currently, DNN-based methods have outperformed other types of semantic similarity matrices. So what's the weakness of those constraints? First, the changes will easily vanish when the whole sentence is relatively long. For this one, we can extract the changes using Lorentz distance. Second, the embeddings of antonyms cannot be distinguished. The solution is to get the word embeddings via a model that is based on contrastive learning. In this way, the semantic similarity information can be learned during the training process of the model. Third, sometimes a word can have different meaning depending on the context. As for this one, we extract not only the changes themselves, we also extract the surrounding words. Here comes the research question 2. We want to validate whether the proposed matrix can outperform other existing matrices. For our evaluation, we also include another check of matrix, that is neuron coverage. The intuition behind is that if 2 sentences are close in the semantics, the activated neurons in the neural network should have something in common. To be specific, we compute the number of neurons activated by the original text, but not the generated test case. For the evaluation, we compare the similarity matrix with the human evaluation score. From the results, we can see the proposed method achieves the best average performance. Surprisingly, we can see that the performance of many semantic similarity matrices is lower than neuron coverage-based matrices. All in all, the proposed method can detect those false alarms and outperform other baselines in most of the experiments. There are some takeaways from this experiment. First, existing semantic similarity matrices are weak in a scenario where 2 sentences differ in just a few places. Second, existing methods compute cosine similarity or Euler distance, neglecting the power of neuron coverage. Next, we want to find out how the metric can help in practice. In particular, we are curious about these 2 research questions. Research question 3. Can the proposed matrix filter out bad quality ones with high quality ones remained? Research question 4. Can the proposed matrix improve the robustness of existing NLP software? For RQ3, we filter out test cases with low scores and asked the annotators to evaluate the quality. Here is the comparison before and after the filtering. We can see that the annotators give higher scores of consistency and naturalness, while finding less false alarms. In conclusion, the proposed method can filter out low-quality test cases, preserving high-quality ones. It can facilitate NLP software testing by selecting those good test cases, saving developers time. To answer research question 4, a common way to improve the robustness of NLP models is robust training using the found bugs. In other words, we add the test cases which made the model fail to our training set and retrain the model. Unlike in CV field, robust training in the NLP field is shown to be able to improve both test accuracy and robustness. The goal in this experiment is to check whether the test cases selected by our matrix can gain further improvements. We designed 2 training settings. In setting 1, we randomly select the test cases to the training set. In setting 2, we sort the test cases using the proposed metric, and we use just top ones to add to the training set. Next, we prepare different training sets using the amount of 5%, 10%, and 15% the size of the original training set in both 2 settings. Finally, we fine-tune a BERT on the prepared training set. The experiments are done on the movie review dataset. We evaluate the robustness using an attack method called PWWS. This is the result of the 2 training settings in terms of the accuracy on the test set and the attack success rate of PWWS. Note that the lower the attack success rate is, the higher the robustness of the model is. The blue line is the first setting, which uses random test cases. The red line is the second setting, using the selected ones by our matrix. We can see the overall trend of both accuracy and robustness is first improve, then degrade. The reason is that there are noises in the test cases found by current testing methods. The most important thing is, using the test cases selected by our matrix, we can gain further improvements on accuracy and robustness. The results show that our method can save the training resources and time when we do robust training. In other words, most of the test cases are not needed. There is also a lesson learned in this experiment. Using test cases with a size of 10% the size of the training set is the best, validating results from previous papers. In conclusion of this work, we find many false alarms in current textual testing methods, which means NLP software is more robust than we thought previously. And existing similarity matrices cannot deal with sentences that differ in just few places. Finally, high-quality test cases further improve the accuracy and robustness of NLP models, and using 10% of the training set size is the best. This is the end of my presentation. Questions are welcome.